and I've got a cantaloupe sitting on a table. So this cantaloupe sitting on a table, you know what? I'm going to start off by doing a free body diagram. And actually, before I do a free body diagram, I really should be good about this and give myself a reference frame. So up, down, positive, negative, sure. But if I'm going to do free body diagrams for this, I'm going to have to talk about the cantaloupe as its own free body diagram. I'm going to have to think about the table upon which it sits as another free body diagram, and think about the Earth itself maybe even as its own thing. And before I start doing free body diagrams even, maybe I should finish this sentence. It says, for every action force there is an... You guys know how to finish this? Let me try again. For every action force, there is an equal and opposite reaction force. And like, at some point here, I'll finish it off. An equal but opposite reaction force. And at some point in my childhood, I watched a cartoon, I'm sure of it, where somebody, whether it was like Dexter's Lab or Mr. Peabody or somebody or other, said this just to prove that they were the smartest person in the room, right? So this is kind of like a common cartoon trope to say Newton's third law, just to establish yourself as the smart person. Okay?
For any student that hasn't yet to have their photo taken, please make your way to the cafeteria.
So let's talk about how this is going to play out. First of all, let's think about the cantaloupe. One thing that I know for sure about cantaloupes when they sit on tables is that they experience gravity. Agreed? Right. So I got a force due to gravity acting down on this cantaloupe, and I might say force of gravity. And you know what? There's going to be a cantaloupe, a table, and the Earth here. And so I actually have to come up with this notation. And in case you didn't catch it before, I actually did use it once before. FG.C. Now when you see a dot, I'll put it up here, and this seems like a weird way to say it, a little bit awkward, but in quotations, a dot in force notation, force variables. Oh, my pen is dying. I'm going to have to switch over to another pen. Variables. The dot means, I'll put it in quotes, acting on. Okay, end quote. So if I'm talking about FG.C, the way I would read that is force of gravity acting on a cantaloupe. Okay, cantaloupe's kind of melon in case you don't know. Remember, the dot means with respect to or relative to when it's a velocity vector. So it's different code. It's different code for a different kind of vector. That's all it is. Okay, so for forces acting on. So there's a force of gravity acting down on this cantaloupe, and knowing what I know about cantaloupes sitting on tables, what's holding the cantaloupe up? Yep. Oh, I'd like to call it a normal force, but like what object is holding it up? A table. A table is holding it up. So I would say that I've got a force of a table acting up on a cantaloupe. And you're right, it is a normal force, but I'm being really nitty-gritty. I'm being picky about this. There's a table acting up on this cantaloupe. But Newton's third law says every action force has an equal but opposite reaction force. So if there's this action force of a force of table acting up on a cantaloupe, what do you think is happening to the table? Look at this sentence. Yeah?
It's being pushed down.
Yeah. It turns out that there's a cantaloupe acting down on a table. Look. This is the cantaloupe's free body diagram. This is the table's free body diagram. There's a cantaloupe acting down on this table. Now somebody else might say, oh, wait a minute, isn't gravity acting down on the table? Well, yes, also. And also, gravity is acting down on the table. Okay? There can be both. If there was no cantaloupe, wouldn't the gravity still be acting down on the table? Yeah, of course it would be. But in this case, there's a cantaloupe and the gravity acting on the table, pulling down on that table. And I know that the table doesn't crash through the Earth, because I've had this exact same situation play out in my kitchen before. So what's holding the table up? What was that? The Earth. The Earth is holding the table up. Yeah, you know, and I don't know if you can tell under my camera or not, but this is green. Can you guys tell that that's green? All right, so that's green. I've got a force of the table, I'm going to be careful about this. I'm going to make this really big. Can anybody tell me why that's really big? Think about what's happening to the table. Is it going up or down, or is it staying put? Why did I make the green one really big? Yeah. Yeah, it's going to counterbalance those two forces. You're right. Okay, so I like the call that there's the force of the earth acting up on the table, but it's going to have to be bigger than the other two. In fact, going to counterbalance the other two, because I know the table stays put. Now, if there's a force of earth on the table, what also has to be there according to Newton's third law? Imad, what do you got? What's that? No, forget about the cantaloupe. Yeah. Table acting on the earth. Turns out that that table presses down on the earth. Oh, I should make it the same size, because the rule is equal and opposite, right? So there's this other thing that people talk about is Newton's third law, action-reaction force pairs. And I've tried to color code this. Can you see that the green ones are pairs? They're equal and opposite. The red ones, they're pairs. They're equal and opposite. Each half of the pair doesn't get attached to the same object, though. One gets attached to the cantaloupe, the other one gets attached to the table. See what I mean by that? For every action, there's an equal but opposite reaction force, but they're attached to different objects. And you can even see, look, this one ends in a T and starts with a C, this one starts with a T and ends in a C. You notice that all of the forces acting on the table, though, end in T? Because those are all the forces acting on the table. Stands to reason, right? Like, that's not rocket surgery. Now, the thing is, when I look at this Earth, I think, well, wait a minute, why doesn't the Earth fall down out of the sky? That's kind of a question that I don't really love addressing. It turns out that it's a really good approach to have a nice free body diagram of the cantaloupe, of the table. Can we just acknowledge that the Earth isn't just like one object, really? Isn't there like an outer layer, and then there's like lithological, or whatever you call them, geological layers to the Earth, magma, the mantle, like all that sort of thing? Isn't that kind of like a table on top of a table on top of a table on top of a table, and it just kind of goes down, 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 until eventually you get down to like some solid iron core that's like this magnetic field source for our Earth's magnetic field as it spins or whatever. I don't know. I'm not a geophysicist, but the idea here is that we have actually like a lot of tables. And so it becomes problematic to think about the whole Earth in this way, like as a free body diagram, because we would just have like this unlimited number of tables almost, like as we go through the stratified layers of soil. So I don't want to really go down that path. I want to recognize that, yeah, okay, there would be like a whole bunch of other soil stratifications or rock stratifications pushing up on this thing. But I feel like that being the case, and me understanding a little bit about geology, I'm going to put a little box around the Earth and say, you know what, I think I'm going to just avoid going down that particular pathway, because I recognize that maybe not fruitful. Okay? So I'll just think about these things that are sitting on top of the Earth as I think about this free body diagram, because I think that's going to be fruitful for me. When I look at this picture of the cantaloupe above the Earth, though, you see this is like a cantaloupe. It seems like it's a cantaloupe orbiting the Earth, like the way it is. But like as I look, and that would be kind of a weird satellite. But anyway, even if I had a cantaloupe orbiting the Earth, there would be a force of the Earth acting on the cantaloupe. I mean, it's doing so by gravity, isn't it? It really is gravity that's causing that Earth acting on cantaloupe. And it stands to reason that there must also, although the resolution doesn't really show it very well here, we really should say that there's a cantaloupe acting on the Earth. Because something that they don't usually tell you when you're a little kid, well, maybe they did, depends on the people you talk to. But if the Earth exerts a force of gravity on you, did you know that you also exert a force of gravity on the Earth? You're attracted to the Earth, but the Earth is also attracted to you. Now the thing is, you're so small. You're going to notice that force of attraction. The Earth is so big, it's not going to notice the force of attraction. I mean, think about it. These two forces are actually the same magnitude. But if I do this, if I say, this is the force of the Earth acting on a cantaloupe. This is the force of a cantaloupe acting on the Earth. Notice those F's are the same size. And that's equal to, remember, Newton's second law, F equals ma. Earth acting on a cantaloupe. Well, a cantaloupe's got a little tiny mass. Doesn't that mean that it's going to have a really big acceleration for a mid-sized force? But the Earth has a really big mass. Do you think it accelerates towards the cantaloupe very much? In fact, that m is under-exaggerated. The acceleration is going to be like smaller than I can even make with a dot there. That little dot there is the tiniest little acceleration. I can make it look like an A just to satisfy you, but the point is that acceleration is so negligible, the Earth doesn't accelerate towards me very much, which is why when I jump up, I notice that I accelerate back down again, but I don't notice the Earth accelerating towards me. You follow what I mean by that? Because the math's imbalance, not because there's a difference in the forces. The Earth is just as attracted to me as I am to it, but our masses are not the same. Okay? It's like basic little logic, I suppose, but it's something that they don't really talk about with the little kids because we're worried about them getting lost on the big ideas there. I want to take a look at something that's more down to earth, though. Somebody pushing a box. So I want to make a little statement. Objects acting on each other should be touching unless a field is involved. Okay, in other words, we're going to have to touch the box to move the box, unless we use a magnet. We're going to have to touch something to pick it up or put it down, unless gravity is what's doing it, okay? So for us, unless you're a Jedi, you're going to move things by touching things. You're not going to use a force, right? May the force be with you and also with your spirit. Anyway, so I've got a person pushing with their feet, pushing a box, okay? And you know what? Before I go any further, maybe I should be good about this. I'll give myself a reference frame. Up, down, right, left, positive, positive, negative, negative. And you know what? Just because I don't have to keep on drawing that again, for the purposes of this page and this page only, I'm going to let that reference frame stand for each of the diagrams below. Okay? So I won't draw that again. I'll just say that's for the whole page. But you know, if I wanted to draw a free body diagram for this situation, or a series of free body diagrams for this situation, I might have a box or a free body diagram for the person. P stands for person, by the way. I might have a free body diagram for box 1. I'm labeling it box 1. For box 2, and this is a person pushing on a crate that's butting up against another crate. So box 1 butting up against box 2. And if I do a free body diagram for these things, you know what? I think I'm going to start with box 1. And if I start with box 1, easiest thing, force due to gravity acting, sorry, not box 1, box 2. Force due to gravity acting on box 2. And people always say, start with the easy stuff, start with what you know, and then go from there. If there's a force of gravity acting on box 2, isn't there also going to be a force of normal acting on box 2? And so, yeah, I am going to fall back to calling it not Earth on 2. Let's call it normal on 2, because I don't want to have to deal with a free body diagram of our planet, you know? And, you know, if you ever go to the orchard, they always say, pick the low-hanging fruit first. So the easy stuff, force of gravity on 1, force of normal on 1. Force of gravity on the person, force of normal on the person. Okay? That's the low-hanging fruit, the easy pickings. But I want to take a look at this mass 2 and say, hey, well, what's pushing mass 2? Is it the person? What is it? 1. Box 1 is pushing back box 2. So I could say I've got a force of 1 acting on 2. Newton's third law, action-reaction. What's the other half of this action-reaction force pair? Yep.
If the first box is pushing on the second box is pushing on the first box.
Right. If there's a force of 1 pushing on 2, there must be a force of 2 pushing back on 1. That's reaction force. Equal and opposite. I'll even color code it. I'm doing it in orange so that you can see the matchup. Okay. So force of 2 acting back on 1. a resistive force, if you like, right? And as I carry across here, you know, maybe I'll grab myself another color, try and use green again, see if it shows up. Seems to me, I don't know if you can tell that's green, that one's a little bit of a darker green. I could talk about force of a person acting on one. I couldn't draw a force of person acting on two, because does the person touch two? No, sir. But if there's a force of person acting on one, what's the other half of that action-reaction force pair? Yes, sir? Yeah, force of the one acting on the person, opposite direction. See how they come in pairs? Equal but opposite, never attached to the same object, always opposite direction, always equal in size. Okay? We're talking about like Star Wars and the Force be with you. This is like the Sith. They always come in pairs, you know? Where there's one, there has to be another. Okay. So, I don't know, that's dorky, I'm sorry. I regret saying it even. So, the other thing is, I noticed that this person here that's pushing on the box, notice that right now it looks like they're going to slide to the left. Well, that's not the way I've experienced boxes before. It turns out that there's something happening at the people's feet. And that something that's happening at the person's feet is called traction. Traction. And traction is literally what allows us to push stuff, right? Without having the feet slip out from underneath of us. We can say traction, non-slip. And if something's not going to slip, what we're really talking about is this person being able to grip the floor because of static friction. Okay? And so people say, what? You can push boxes because of static frictions? Well, heck yes. The box slides. But because of static friction, you doesn't. Right? You don't want to slide while you're pushing the boxes. That's why you have treads on your shoes. That's why if you have the fancy socks with the, you know those little sticky rubbery things on the fence of the, you know, like the fancy socks people get sometimes? It's also why we invest a lot of money in tire tread design, even winter tires, because traction, non-slip, is really important if you want to be able to pull a trailer, push a snowplow, whatever it is, right? Not slipping is important. If I want to push boxes too, though. And, you know, even if I zoomed in on this thing, here, I've got a person's shoe here. You'll be able to tell it's a shoe in just a second. There's the laces, boom, boom. A little bit of tread on this shoe, crisscross, applesauce, a little bit of ankle, not too much ankle. Go up here, oh, knobbly knees. Okay, so we got this foot, and this foot's walking along. And as this foot walks along, one thing that I know, really we've just done a zoom shot of this person's foot. As they zoom in there, you know that when you walk, don't you push the ground underneath your feet backwards? It's true, right? That's what the traction allows you to do. And what we would say is that there's a force of the shoe acting on the ground. That's you pushing the earth backwards. But the reaction force is the force of the ground pushing your shoe forwards. We need action-reaction forces. We need traction to walk. If you didn't have action-reaction forces, you couldn't walk across the room. True? That is a fact, right? We need Newton's third law just to move around. So I'm just highlighting that this little bit here, even though I can't see what's happening in this zoomed out shot, I'm zooming in to acknowledge that even that is actually an action-reaction force. But the thing is, that's a little bit complicated for most people to want to, you know, really trouble themselves with most of the time. So really what they'll just say is, this person is able to push with an applied force. Okay, so we got an applied force. And we just say like, this big umbrella term, somehow the person's feet's able to apply a force on them. And we're all cool with that, okay? Just a little, you know, general phrase. And it just means we don't have to discuss the nitty-gritty of traction. Everybody cool? Keep on moving. We've got another person here. This person's a puller. That other one was a pusher. Before we get into the pushing issue and the pulling issue, let's talk about what tension is. Tension is an action-reaction force. Okay, it's a Newton's third law force, where a lot of the time you get people that will write it as F subscript T. Or sometimes they'll just forget about the F and write a capital T. I write F subscript T. And I want to point out that that tension force is equal to the magnitude of force of 1 acting on 2. See, look there. That little rope right there, we're talking about the tension that's being exerted through that little rope right there. And that's equal to the magnitude. Remember, magnitude means we just talk about how big it is, not positive or negatives, not direction, just how big. In other words, the amount of force, the amount of tension that pulls on 2 to the right is the same amount of tension as the amount of force that pulls 1 back to the left. And we just say that it's a magnitude. We call that the tension, okay? Anyway, when I look at this situation, I want to free body diagram this thing out. I say, okay, that's box 2. That's box 1. Here's our person. P is for person. You can make P stand for anything. It could be pal, it could be Patrick, whatever you like, okay? It's a person, though. And again, always pick the low-hanging fruit first, okay? FG acting on 2. But I can't just call it FG. My goodness, don't just call it FG, because there would be 3 FGs. We got to specify that this is FG2, FG1, FGP. Be specific. And a lot of people early on in the course didn't believe me that I wanted you to be really particular about your variables. Believe it now, okay? We really got to be on this. And then, of course, for the same reason, I'd have F normal 2, F normal 1, F normal person. Now look at that normal person, okay? Patrick, a normal person. All right? Carson maybe doesn't agree. We'll leave that up to these gentlemen. All right. So I always wonder about Carson. Like, like from a Nordic naming perspective, the son of a car. I like it. Makes you sound powerful. All right, so I got these free body diagrams. I'm not totally finished with these things, though. I got to think about the horizontal stuff. And again, I'm going to color code this stuff. I think that there would be a force of 1 acting on 2. And I could even acknowledge that that's going to be a tension force, right? But if there's a force of 1 acting on 2, what else do I have to have? 2 acting on 1. You better believe it. Equal in size, opposite in direction, not attached to the same object. And what about this guy here? What could be acting on this guy that I'm missing? Yeah?
The person pulling.
Person, yeah. The person is actually attached to this one.
Would that be 1P, F1P?
This would be FP1. You got to read it from left to right. Force of the person acting on 1. Okay? Order matters. And if there's a force of person acting on 1, stands to reason that there's a force of 1 pulling back on the person. And anyone who's pulled a little red wagon knows that this is true. The wagon resists. It pulls back on your arm, Now again, and I can acknowledge my little shoe again, I'm not going to talk about traction. Nobody wants to go down that rabbit hole. We're just going to agree again that's an applied force, right? That's allowing this person to do their pulling. So we're going to say we've got an F applied going this way. Okay, and really it's being endowed to the person by virtue of traction, right? And their ability to push with their legs. Now, if they push with their legs harder than static friction will allow, aren't they going to spin out then? So there's a limit to how hard you can push. Not just the limit of how hard or how strong your muscles are, but how hard you can push before static friction won't push back on you anymore, right? And we see that with cars. Now let me draw a car. If I have a sedan, like one of these, sedan, got some wheels here. Put my car on the road, make it be a front wheel drive. Front wheel drive. Did you guys know when you drive your car, think about it kind of like the running shoe. When I drive my car, didn't you know the purpose of your wheels is to push the road backwards? That's what wheels do. They push roads backwards. And so if we wanted to think as Newton's third law people, if you push the road backwards, that would be the force of car acting on road. But that's not what actually makes the car go forward. Isn't it the reaction force that drives the car forward? I one time heard somebody say, roads propel cars, while cars propel roads backwards. Does that make sense? So I got force of road acting as a reaction back on the car because of traction. Now you can mess this up. If you want to eliminate the action-reaction force pair, you can go out to the intersection outside the school. You could take a big old barrel of oil and spill it all over the intersection. Would you be able to get a reaction force then?
No.
No. You would also cause a lot of bodily harm as people crash. Don't do it, okay? So I'm not saying you should do it. I'm saying that we would eliminate that action-reaction force pair, and it really underscores the fact that we need a reaction force to get cars to go somewhere, right? We really do need that reaction force, and the ground's able to supply it, but as soon as you lubricate the ground, it can't supply the reaction force. Okay, so that's an important thing to sort of notice there. We don't want to spin out, and the fact that we don't spin out tells us that there's a reaction force there. Now I got this horse, and I want to brag. You know what? I drew this horse in Google Drawings. Isn't that beautiful? Like if you drew that horse, wouldn't you want to show people? Look at the stick man horse. I used the curve tool. Isn't that cute? Anyway, looks like a horse, right? Like, honestly, gonna say it's my best drawing ever, but it's the kind that I would want to give to my mom. Put a little heart on it. There we go. All right, so I got this horse, and we can dress this up and say there's hay in it or something like that. Hay in the cart. But if I was going to do a free body diagram for this one, I could do my horse, put a little H on it, do my cart. That's what we're going to call this. We're going to call this a cart. Okay? Always pick the low-hanging fruit first. Easy stuff, easy pickings. Force of gravity on the horse. Force of gravity on the cart. Force normal on the horse. Look at that normal horse. Force of normal on the cart. What would the action-reaction force pair be for this one? Matt? Well, it's going to be connected to the tension. The tension is going to be the story that we're telling for sure. What would the actual pair be? What would those two forces be, and what would we call them? Yep. I like it. Thanks, John. So, force of the horse acting on the cart. Notice that it's acting on the cart, so I have to have dot C on that one. And then John says there's going to be a force of the cart acting back on the horse. Dragging that horse back, keeping it from really getting away. That's why we attach the horse to the cart. And we could say tension. I'm not quite sure what this material is made out of. If it was a rope, okay, but I haven't actually seen horses tied to carts in this way. It's usually been some sort of harness system. But yeah, it's like some sort of a action-reaction transmission material, right? Like whether it's wood or rope, I don't really know. I'm not a farmer from, 500 years ago. But I just, I believe in this, okay? This is a thing that could happen. All right now it looks like if I don't do anything else, can you guys see that the horse cart system is going to implode? So something's missing here. Right now they're going to get sucked together, right? So what am I missing? Yes, sir.
I'm guessing you're missing the horse going forward.
Right, okay, so this horse, yeah, we called it applied, just like we did with humans and cars. We might call it an applied force, and really that's coming from the traction at the horse's feet. That's fine. Now, something that I haven't talked about is friction. And when people draw these things, they'll often say, hey, this cart really should have friction acting on the cart. And then when you press them on that, you say, well, where is it actually coming from? Where is that friction happening? Sometimes they struggle to know where. I want to point out that it's not here. It's not where the wheel meets the road. If it was where the wheel meets the road, if that's where kinetic friction was, wouldn't that not be a cart? It would be a sled, right? The wheels would have locked up. We'd be sliding a bunch of hay around in a box. That's stupid. That's hard on the horse. Don't do that. Be kind to a horse, right? That's why we invented the wheel, was to make things easier. And actually what wheels do is they do a stick and roll. In fact, it doesn't slip. It sticks, and then the next piece of the wheel gets exposed to the ground, and then that sticks, and the next piece of the wheel gets exposed to the ground. It doesn't slide, it sticks and rolls. That's what wheels are designed to do, right? So then where's the friction coming from? Clearly, it's not frictionless. Where's the friction exist? Yes, sir? It's not static friction, because there is kinetic friction. Can I tell you where it is? It's not the horseshoes. The horse isn't sliding. It's actually happening right inside the axle. All right? So what you would do, imagine yourself. You're 500 years ago. You want to move a bunch of grain from one place to another. You're going to make a box. You're going to strap a box to a large animal, maybe a horse. And then you're really keen on wheels. Let's slap a couple of wheels on the bottom. And the way you're going to attach these wheels is you're going to have some sort of, maybe you're even good at metallurgy, or somebody in your village is. You're going to put a mount on the bottom of your box, something like this. You'll bolt it to the bottom of your box, and that's going to be the axle mount for the bottom of your wagon. You're going to slip an axle through it. Now, depending on where your society is at, you're going to have a metal axle or you're going to have a wooden axle. But no matter what kind of axle it is, as this thing spins, isn't it going to rub? That's where the kinetic friction happens. The kinetic friction happens right there, right where the axle, right where the axle rubs against the axle housing. That's where it's going to happen. And so people say, well, how are you going to deal with that? We don't want to have friction. We'd like to get rid of friction. What do you think the people in that society would probably do? Yeah. What's that? Oh, they wouldn't have had bearings yet. Something even simpler. Yeah. Well, not water. Water's going to cause more rubbing. Oil. Oil is probably the best bet. So we're going to inject a lubricant. And whether it's a plant-based oil or an animal-based oil, I wouldn't really want to use an animal-based oil in my farm personally, because you got like rotten, cattle fat or something in there. That sounds disgusting on a hot summer's day when I'm moving my grain. I would probably want to use like an olive oil or like, a corn oil sort of thing if I have access to it. But whatever it is, I'm going to use some sort of a grease to make sure this thing spins nicely. And actually, I like the way you think, because a few years later, people with better technology came along, and actually this is what we use today. We'll actually, Imad says that we're going to put bearings inside. Yeah, ball bearings. And, like for years, my dad, he was a geologist, and then he was a bank manager, and then he was an engineer. And he would go around and they would make, he just liked to do a lot of things, right? And so one of the things he did was sell automation parts for assembly lines. All the time there were automation for assembly line component parts in my garage as a kid, like parts that he was selling to different places, a lot of German engineering. And inside of these things, there would be ball bearings and other spinning parts so that the spinning parts could roll against the ball bearings. And now we got little balls, highly polished, low friction balls, and axles rubbing against each other. And even then, they would inject lubricant in there so that the balls could roll even better, right? So we always get in the lubricant, and really the lubricant's in there to diminish friction. So let's make a little note of that. Ball bearings to minimize friction. Okay, that's where the FK is happening though. Right in the axle. It's not because the wheel is sliding like a sled along the ground. Okay. Oh, hey, one little thing before we leave this page, and you can zoom in if you're looking at it on a YouTube video, or you can just look at it on your page if you're in person. This is like the easiest street language way that I can express Newton's third law. And I'll read it out loud. You can't push or pull on something unless that something simultaneously pulls or pushes on you. That's the law, okay? But we have it more formally at the top of the page, and we kind of talked through it a bunch here.